All right. Welcome to session 9. So, this session is titled Evaluating Transparency and Explainability, which is XAI for short. This session will focus on how we can assess whether AI systems are transparent and understandable to humans. It's an important step towards building trust in AI. Let's get started. Okay, so let's start with a quick overview here. So today's session is about opening the black box that we have talked about multiple times throughout the previous sessions, the black box of AI systems. You have probably heard of the phrase black box, right? It's the box or the closed system that you don't actually know how it works from the inside, but you know what inputs are getting into it and what output is producing this black box. So yeah, we've talked about it previously in data sets and we have cracked it. So now we will talk about it throughout the AI itself. So it describes how AI models, especially complex ones like deep learning systems or large language models, can make decisions that even their creators they struggle to fully explain. We see an output, but the reasoning behind it is hidden. So think about this one. In real world example. So imagine a medical chatbot that suggests a treatment plan or a financial one that denies a loan, just as the examples that we've talked about before. Even if those systems are highly accurate and fair and secure, users will hesitate to trust them if they don't understand why. If they don't understand why those decisions were made. That's where transparency and explainability come in. Together they form that what we call explainable AI, or for short XAI. These ideas help make AI's reasoning visible, understandable, and justifiable, not only to developers, but to the people affected by its decisions. And this isn't just a technical goal, it's about accountability and fairness and even legal compliance, especially in high stakes fields like medicine and finance, etc. So, in this session, we will learn how to look inside this black box to understand not just what a chatbot does, but also why it does it. Let's move on to the next slide. It's actually a short session today. It's fun. It's about some not fully technical, but more like a theoretical principles, which are transparency and explainability. Okay, so yeah, now we've set the stage. Let's dig into what we actually mean by transparency in AI systems. Transparency isn't a simple yes or no property. It's not that a system is either open or closed. It's more like a spectrum with different layers that we can evaluate. So we can think of transparency as the three main levels. Let me start. Okay, so the first layer is design transparency. This is all about how well the system is documented. Does it clearly describe its architecture, data sources, and goals? For example, if a company releases a chatbot, we should be able to see model cards that describe what it was trained on, what data sets or data sheets that it was used in training this model, etc. So Also, yeah, about the data set, we should know where the data came from, and what biases it might contain. That all, if that documentation is missing or even vague, that's already a red flag for transparency. So yeah, this is the we can call it a pre transparency. We have also the model transparency. This focuses on how understandable the model itself is. Some models like decision trees or linear regressions, those are some algorithms. I'm not sure if you heard of them before. They are some algorithms that are used into training the AI model. So a decision tree could be something like this. This is a let's say a function or a call, and it has um, some, what is it called, branches. Yeah, so a branch could be anything. Let's say if this one is could it rain or something like this. Um, so could, sorry for that. Could it rain? Okay, remove this. Remove this. So just 1 second, please. Okay, I'm with you guys. So yeah, we were saying here, um, okay, let's say if we are asking a model, an AI model, could it if it's going to rain, could it rain? And the branches would be a yes and a no. So this is a really simple structure of a decision tree. It's much more complex than this, but just to understand the structure. So yeah, the decision tree or even linear regression, those algorithms are easy to interpret. Sorry. We can trace exactly how they reach an output. Those are called white box models. But other systems, like deep neural networks, are much more complex than that. They make highly accurate predictions, but it's extremely hard to explain the why. Those are the black box. So, what a deep learning? Okay, can I just move this? Okay, so a deep learning model is something like nodes and nodes and lines. So it's something like this. So this is the input. The input goes through some statistical and fully mathematical um, a process. Oh, it just branches into two layers, also, and those layers also branch into other two layers, and so on. So this branch, it could reach a very large set of nodes. It works, if you have been into biology field, it's just like the neural system of the human beings. So yeah, this one is very it's much more um what's the word, complex to deal with. So this one, even the developers themselves, they don't actually understand what kind of a specific math is going through these nodes. So yeah, finally we've got the explanation transparency. So this is where explainable AI or XAI really shines. Even if the model itself is a black box, we can use external explainer systems. tools that generate human-friendly explanations for specific decisions. For instance, a credit scoring AI might provide a simple reason, like loan denied due to low income to debt ratio. That's explanation transparency in action. Okay, and yeah, here's the key part. When evaluating transparency, we often start with the documentation. If the documentation is incomplete, inconsistent, or overly technical, that's a sign of poor transparency, and it could even indicate ethical or legal risks, especially in regulated domains. Okay, so let's move on. Yeah. Now that we know what transparency means and the layers, let's talk about how we can evaluate the quality of explanations that the AI could produce. Okay, a good explanation isn't just about sounding smart or technical. It has to be meaningful and useful to humans. So how do we tell whether an explanation is good or not? There are a few key criteria here. So the first one is fidelity or faithfulness. This means that the explanation should actually reflect what the model did internally um, do. So if an explanation simplifies or distorts the reasoning too much, it can mislead users, and that is actually dangerous. For example, if a medical AI says it made a diagnosis based on general symptoms, but actually relied on patient age or gender, that's not faithful or even reality. Okay. Next, we've got the intelligibility. This is all about how easily the target audience can understand the explanation. A developer might want technical details, while a doctor or an end user needs something more intuitive. The same explanation does not fit all audiences. Also, we've got the actionability, the third one. A good explanation helps users do something with the information. It should guide them to take a next step or make better decision. For instance, if a chatbot explains that it rejected a request due to missing information, the user should know what to add next time. Okay, so we've got that comprehensiveness. This one means the explanation should cover all important factors behind a decision, not just one or two. If an AI approves alone, users should understand the main variables involved, not just a single data point. Okay, so completeness, the last one, a complete explanation also includes the model's confidence and uncertainty. This helps users understand how reliable that output really is. So, for example, if I said I'm 80% confident in this prediction, this one tells you a lot more than a simple yes or no. Okay, how do we evaluate these qualities? Often, researchers run human studies. They show people multiple explanations for the same AI output and ask which one feels clearer, more accurate, or even more useful. Okay, so that feedback helps measure which explanations are genuinely effective for real users. So it's all about the system. Okay, let's go on. Let's look at how these explanations are actually generated. So, explainable AI or XAI, it uses different techniques to help us peek inside the model's reasoning. Um, Broadly, these fall into two main categories, and the first one we will cover is local explanations. Local explanations focus on a very specific question. Why did the model make this particular decision? In other words, rather than explaining the entire model, they explain one output at a time. So let's go through a few common techniques over here. First, we have feature importance or saliency maps. These highlight which parts of the input had the biggest influence on the model's decision. For example, imagine a sentiment analysis chatbot. The user says, I'm very angry, the customer service was terrible. This system decides negative sentiment for this one. The explanation would highlight the words angry and terrible over here. Okay, so these are the entities of this sentence. It highlights the angry and the terrible words as the most influential features. This helps us see what a model paid attention to. Next, we've got the Lime and Chap. So they are two of the most widely used explanation tools. Lime is short for local interpretable model agnostic explanations. It works by slightly tweaking the input and observing how the output changes. It's like gently poking the system to see how sensitive it is to different parts of the data. So, as a reminder here, we don't really understand what's inside the black box. So we kind of play with the prompt. We just slightly like change words or change the sentence order or anything just to see how the output is produced when we do this. Okay. On the other hand, SHAP stands for Shapley Additive Explanations. It's based on the concept of Shapley values from game theory developed by Lloyd Shapley. This idea is to fairly distribute credit or responsibility in quotation among players. To distribute credits among players in a cooperative game. In the context of AI, each feature in the model is treated like a player in the game. The model's prediction is the payout. SHAP calculates how much each feature contributed to that specific prediction by averaging overall possible combinations of features. So yeah, okay. And we've got the counterfactual explanations. These are especially powerful because they show how a small change in the input could change the outcome. Let's say the input is, I want to close my account. The model routes it to the account closure department. A counterfactual explanation might say, if you had said, I want to temporarily close my savings account, your request would go to a whole different apartment. That helps us. That helps both users and developers to understand where the model draws its boundaries and how its decision logic is working. Local explanations like these are extremely useful because they make individual AI decisions traceable and testable, and importantly, understandable to humans. Okay, let's move on. Okay. Now, let's zoom out and talk about global explanations, which answer a bigger question, which is how does the model work overall? We've we've just been um, let's say we've just been hitting around the bushes as I forgot the saying. We didn't really we haven't been into the core of the AI. We will talk about it briefly right now. So yeah, global explanations gives us a bird's eye of the a bird's eye view of the model's general behaviors. Instead of focusing on one prediction, they help us understand patterns across many decisions. One common approach is example-based explanations. Here, the system explains its decision by pointing to examples from its training data. I think this one is hiding. Okay. So yeah, we're here. The system explains its decision by pointing the examples in a training data. One common I'm sorry. For instance, it might show prototypes, examples that represents the most typical cases for a certain category, and it can also show criticism, examples that are outliers or case that the model finds confusing. So, okay, let's imagine we are evaluating a chatbot that classifies customer messages. A prototype might be a message like, I need help with my order, something the model confidently routes to the support team. A criticism might be something like, I'm unsure if I should cancel my order or just return it. So here, the model hesitates to or performs inconsistently. By comparing these two sentences, evaluators can understand how the model learned and where it might still be uncertain. It's about the evaluation. We've talked about this before. We've got multiple steps and multiple sources of evaluation. Okay, another important method is rule extraction here. This involves approximating a complex model, say a neural network, just as the one we talked about before, with a simpler and a more interpretable one like a decision tree. So the idea is to translate the model's internal logic into a set of human readable rules. For example, a rule extracted from a chatbot might say if the message contains the words invoice and error routes to it will route it to billing. If evaluators can then test how closely this simple and transparent model mirrors the original one. Global explanations are powerful because they don't just tell us how about they don't just tell us about one case. They help us understand the model's overall reasoning style and the logic that it follows to perform those specific outputs. Um, so yeah, it's a broadly one and more helpful than just to trace one input or one output at a time. Okay, so let's talk about one of the most practical aspects of explainability in chatbots: tracing the full decision path. Most chatbots today aren't just a single model. They're actually made up of multiple components that work together. Things like the NLU, the natural language understanding, um, dialogue manager, knowledge base, and of course NLG, which is natural language generation. When we talk about explainability, it's not enough to explain just one part. We have to trace every step from the user's input to the chatbot's final response. So let's look at a simple example over here. Um, okay, if a user asks, "Is the airport branch open on Sunday?" Here's what happens behind the scenes. Let's start with the NLU. So the natural language understanding, the system first extracts the intent. In this case, a request for opening hour, it is a request for opening hours, and then identifies the entities like airport branch and also Sunday, which is the date. So this one is the natural language understanding part. We've got also the KP retriever, the knowledge based retrieval. It searches the correct database or schedule to find the branch hours. So this one is about um, following or I'm sorry, looking through a knowledge base to get a specific information. Also, we've got the dialogue manager. Um, the system here, the system interprets that retrieved information. It interprets them correctly, checking the specific branch's hours for Sunday. And we've got the NLG, the natural language generation. It turns that it turns that internal decision into a clear human response, which is no, the airport branch is closed on Sunday. So this is the full path. Every one of these steps, contributes to the final answer. And if one thing goes wrong, say the wrong intent was extracted or the dialogue manager misunderstood the data, the chatbot could give an incorrect or confusing reply. And this is something we talked about before. The users would lose trust, would be not unsatisfied, etc. And that's why evaluation um, here depends on having detailed logs that capture each stage of the process. These logs are they allow evaluators to trace exactly where an error occurred. Was it a misunderstanding in the natural language understanding, a database mismatch, a misphrased response, for example? By tracing the full decision path, we can pinpoint the weak link and then improve transparency and ultimately make the chatbot more reliable and trustworthy, etc. Okay, we've been moving too fast. Okay, let's wrap up with the big picture. So, throughout this session, we've been talking about moving from a mystery to partnership. Transparency and explainability are what make that shift possible. When AI systems are opaque or they feel like mysterious oracles, they give answers, but we don't know why. That might work for a while, but it doesn't build the trust that users or audience really need. When AI is transparent and explainable, it becomes something else entirely. A partner that we could understand and we could ask questions and rely on the answers that it could give us. Also, explainability builds human confidence, ensures fairness, and helps meet the ethical and legal standards, of course, especially in sensitive areas like healthcare, finance, etc. So, when we evaluate a chatbot, we shouldn't just ask, does it work well? We should also ask, can it justify what it does? A chatbot that can explain its reasoning is one that earns trust, the most trust and accountability. Okay, so in short, this session is or was about bridging humans and machines through understanding, and in the next session we will return to the technical side, focusing on quantitative evaluation, where we will measure performance factors like speed, scalability, and response efficiency. So yeah, that's it for today. If you got any questions, I'm here to answer them. Um, yeah, it's a short one. It's more theoretical. I'm responding to Rashid's comment. It is over. It's a quite fast one, but I'm here to answer any of your questions. So go ahead. If you got a question, I'm right here. You're very welcome. Okay, so welcome. Jesse, are you here? Okay, I guess I can close the session right now. Um, okay, I cannot close it, but you can leave. You can leave. Oh, okay, there's a question. Would you rather have a perfectly accurate chatbot that's a black box or a less accurate one that can explain its reasoning? Um, well, something that I would say the black box over here is I wouldn't really call it a fully black box. It's just math. So if someone can understand this math, it should understand what the deep learning layers, let's say, for example, it would understand what it does. So the black box over here is not fully vague. It just needs the right person to understand what is happening inside this one. So I would say I would choose the black box where it can give me a perfect response or a perfect output because in business world that's what actually matters. And also I don't think the AI could do things on its own. It doesn't have this um geniusness, or like, let's say, the understanding part in the AI isn't understanding. It's just or thinking. It's not thinking like we do. It's just calculations and possibilities that it follows to perform the output. So yeah, a black box is my choice. Okay. Do Lime and Chap have full names? Are they initials? They are short for so Lime is short for 1 second. I keep forgetting it. Lime is short for local interpretable model agnostic explanations, and Chap is short for someone's initial, which is Lloyd Shapley, with its Shapley additive explanation. I think I'm not sure if I understood the question correctly. Okay, thank you very much. You can leave now. Thank you so much.